Hello and welcome to this GeoStudio Tech Talk on heat transfer in a complex geological setting. I'm Catherine Dompierre and I work with the GeoStudio engineering team here at Sequent. Today's webinar will be approximately 45 minutes long. Attendees can ask questions using the chat feature. I will respond to these questions via email as quickly as possible. A recording of the webinar will be available so participants can review the demonstration at a later time. GeoStudio is a software package developed for geotechnical engineers and earth scientists, comprised of several products. The range of products allows users to solve a wide array of problems that may be encountered in these fields, including slope stability analyses, the movement of water, contaminants, air, and energy through the ground, and stress and deformation in soil and rock. This webinar is a continuation of the project from last month's Tech Talk, where a complex 3D geometry was created in GeoStudio. Today we will investigate 3D heat transfer through this geometry using Temp3D. Let us quickly review the project location. Here's the regional geology of our project site in central Alaska, where our building is to be constructed. In last month's Tech Talk, we created the 3D domain using a small portion of the regional geology. The top brown material in our domain represents an ice-rich silt. The top portion of this can be considered an active layer where temperatures fluctuate above and below the freezing point of pure water over the course of a year. Below this active zone is continuous permafrost. Permafrost is a layer on or under the ground surface comprised of soil bound together by ice that remains frozen for at least 2 continuous years. Below the permafrost is unfrozen ground. As discussed in last month's Tech Talk, constructing man-made structures on permafrost, including buildings and embankments, is challenging as heat transfer from infrastructure can melt permafrost, causing subsidence of the ground surface, among other environmental challenges. Buildings constructed as slab-on-grade must employ techniques to minimize thermal impacts, like the series of thermosyphons installed alongside this airport terminal building. Thermosyphons reduce the thermal impact of a building by removing heat from the ground. The two-phase thermosyphon shown here is a passive heat exchanger, meaning that it maintains frozen ground conditions by circulating a fluid without the need of a pump. This fluid is contained in a closed and sealed vessel that consists of an evaporator, which is below the ground, and a condenser, which is above the ground surface. In the majority of cases, the evaporator is sloped to ensure that the condensate flows toward the lower portions of the evaporator. The fluid in the evaporator vaporizes as it extracts heat from the ground. Then it rises up the vessel into the condenser, where it cools, condenses, and returns below ground. This cycle continues while the air temperature remains smaller than the surface temperature, the air temperature remains smaller than a maximum operating value, and the difference between the surface and air temperature is large enough to cause vaporization of the fluid. Our project site includes two-phase thermosyphons, like the one shown here, for mitigating the impact of our building on the underlying permafrost. To model thermosyphons in GeoStudio, we added cylinders representing the evaporators to the project geometry during last month's Tech Talk. The thermosyphon boundary condition available in Temp-W and Temp3D, which computes the convective heat flux using Newton's cooling law, will be applied to the outer surface of the cylinders. Let us review the project in greater detail before starting our work in GeoStudio. In last month's Tech Talk, we created the 3D geometry associated with this project, including the building foundation, consisting of 0.25 meters of extruded polystyrene foam insulation and 1.5 meters of non-frost susceptible gravel. 3 cylinders representing the thermosyphon evaporators were added to the gravel portion of the foundation with a spacing of 3.33 meters on center. One of these is visible on this cross-section. The thermosyphons are sloped 3 degrees from a horizontal reference. They are 9.51 meters in length, 88.9 millimeters in diameter, and are 1 meter deep on average. Each thermosyphon evaporator is connected to a 6.5 square meter condenser. The condenser is not included in the model domain, as the thermosyphon boundary condition accounts for the whole thermosyphon system when applied to the outer surface of the cylinders representing the evaporators. As presented in Part 1, the first step of the numerical modeling procedure is to create the model domain, which we have already done. In today's webinar, we will complete the remaining steps in the numerical modeling procedure, which include defining the project physics by adding analyses to the project file and defining the material properties associated with the model geometry for each of the physical processes selected for the project. Defining the boundary conditions or the external forces acting on the domain. Generating and refining the finite element mesh with smaller mesh in areas where higher gradients are expected. Solving the analysis, and verifying the results by interrogating the model. Let us go through each of these steps in more detail before we open GeoStudio. Once the geometry is complete, we will establish the physics to be solved on the model domain by defining the types of analyses GeoStudio will conduct. This project includes two transient heat transfer analyses. The first is a spin-up analysis used to generate the long-term temperature conditions in the subsurface. This analysis runs for 10 years with 4-hour time steps. The final temperatures from this analysis are used as the initial conditions for the second transient analysis, which evaluates heat transfer given the addition of the building foundation and thermosyphons. This active permafrost protection analysis will run for 388 days, also with 4-hour time steps. The 4-hour time steps were selected for both analyses to ensure convergence is reached. For the material definition, the full thermal material model will be used for the ice-rich silt, as this is the subsurface material of greatest interest in the project file. The full thermal material model requires the definition of a function for the thermal conductivity as the material freezes, as shown here. The thermal conductivity function is estimated using the sample silt material with a frozen value of 2.32 joules per second per meter per degree Celsius and an unfrozen value of 1.49 joules per second per meter per degree Celsius. The change in normalized unfrozen volumetric water content with temperature must also be specified, where the normalized unfrozen volumetric water content is the ratio of the unfrozen volumetric water content to the in situ volumetric water content. You can see here that at 0 degrees Celsius, all of the water is in a liquid state, so the normalized unfrozen water content is 1. As temperature decreases and more of the pore water freezes, the normalized unfrozen volumetric water content decreases. The final inputs for the full thermal material model are the in situ volumetric water content and the frozen and unfrozen volumetric heat capacities as shown here. The remaining materials use the simplified thermal material model where both the frozen and unfrozen volumetric heat capacity and thermal conductivity are specified. Note that an activation temperature is set for all materials to define their initial temperatures when each becomes active on the domain. For the soil and rock materials, this is at the beginning of the initial spin-up analysis. The initial temperature of the silt and underlying deposits is set equal to the average annual surface temperature of negative 1.14 degrees Celsius. The effect of the initial condition is eliminated by solving the spin-up analysis over 10 annual cycles. The gravel and polystyrene insulation are activated at the beginning of the second active permafrost protection analysis. The activation temperature for the gravel and insulation is set to 15 degrees Celsius, which is representative of the temperatures prevailing during the building construction. In the initial spin-up analysis, two boundary conditions will be applied to the domain. On the bottom of the domain, a constant heat flux is applied to represent a geothermal gradient of 25 degrees Celsius per kilometer. Conditions at the ground surface are assumed to be representative of climate conditions in Fairbanks, Alaska. The ground surface temperatures are computed using the air temperatures from Fairbanks and the N factor approach, with freezing and thawing factors of 0.5. In the active permafrost protection analysis, these two boundary conditions continue to be applied to the ground surface and the bottom of the model domain. Two additional boundary conditions are also necessary for this secondary analysis. The first is a constant temperature boundary condition representing the thermal conditions of the building. The temperature inside the building is assumed to remain constant at 15 degrees Celsius, so this temperature will be applied to the surface of the polystyrene insulation. The final boundary condition required for this project will represent the thermosyphons. This boundary condition applies a convective heat flux along the outer surfaces of the evaporators. Air temperature and wind speed at the site over time are required for computing the convective heat flux. The convective heat transfer coefficient evolves as a function of wind speed as shown here. This function is based off the equation presented by Haynes and Zarling. For more information on this equation, please enter your contact information into the question box and I can provide a more detailed explanation. Finally, the maximum operating air temperature and minimum temperature difference for vaporization of the circulating fluid, which is carbon dioxide in this case, are required. The overall element length of the project domain will be set to 5 meters using a hexahedral element type when generating the finite element mesh. However, before we generate the mesh, we will specify the portions of the domain we wish to refine. The upper portion of the domain representing the ice-rich silt will have an overall element edge length of 2 meters. With elements decreasing in size near the ground surface where the mesh will be refined to a length of 1 meter. Further mesh constraints will be applied to the evaporator cylinders and the solids representing the insulation and gravel. The mesh is refined such that areas where greatest thermal gradients are expected, like around the thermosyphon evaporators, have the smallest mesh. The resulting mesh consists of approximately 179,000 nodes and 270,000 solid elements. Once the finite element mesh is generated, locations can be added in the mesh view. These locations are used for creating plots of the analysis results. We will review how to set up locations before solving the analyses. However, this step can also be completed after an analysis has finished solving. This means that if you wish to create graphs at new locations to better interrogate the model results, you do not need to re-solve the analysis after specifying the new locations. After solving the analyses, we will interrogate the results of the spin-up analysis by first checking convergence and ensuring the results make sense given our understanding of the problem. We will then spend more time reviewing the results from the active permafrost protection analysis. We will use the draw graph dialog to review the convergence, heat extraction rates of each thermosyphon, heat flow across the building floor, the change in temperature over time at multiple points below the building, and to create vertical temperature profiles. We can also look at the temperature contours to help us visualize change in temperature through the domain over time. Ultimately, we want to ensure that we generated a converged solution that aligns with our understanding of the physical system. Given this, we can more confidently determine whether or not the thermosyphons were sufficient for protecting the permafrost below the proposed building. Now that we have reviewed the steps for setting up our analyses, let us open the GeoStudio project file. Here we have our project file with the three-dimensional geometry created in part 1 of this webinar series. The steps we followed to generate the 3D domain are listed in the design history of the Geometry Explorer. If I was not the one who generated the 3D geometry, I could review these steps to better understand the project. As I am the one that set up this 3D geometry, I will begin by adding the physics or analyses to the project file by opening the Define Project dialog. In this dialog, I first wish to set the project start date by clicking on the top item in my project tree, going to the Settings tab, and entering 09/01/2011. This means that the project will start on September 1st, 2011, 10 years prior to the construction of the building. The first analysis I wish to conduct is the spin-up analysis to generate typical temperatures through the 3D domain while eliminating the effect of the initial conditions. I will add the spin-up analysis by pressing Add and selecting a Temp 3D transient analysis. I will rename the analysis Spin Up. Under the Physics tab, I see that heat transfer via conduction is automatically applied to my Temp 3D analysis. This is the only physical process I wish to simulate, so I do not need to check any of the other options listed here. However, you can see that we can model a range of different 3D flow processes in a single analysis in GeoStudio. Under the Heat tab, we will leave the initial temperature definition as none, as we are using the activation temperature option available in the material definition. Under the Time tab, I need to establish the time steps. The spin-up analysis will run for 10 years, so I will enter a duration of 3,650 days. I wish the time steps to have an increment of 4 hours. And I only want the results to save at the very end of the analysis, so I will specify that it saves every 21,900 steps, which is the total number of steps. Once the spin-up analysis is complete, a secondary transient analysis will assess the effect of the thermosyphons over a 1-year period with the building base in place. I will add the second analysis to the project tree by pressing Add and selecting a transient Temp 3D analysis. I will name this analysis Active Permafrost Protection. And leave the same physical processes applied to the domain as in the initial spin-up analysis. In the Heat tab, I will ensure the initial temperatures are from the last step of the parent analysis. Under the Time tab, we can see that the time settings of the first analysis were copied to this secondary analysis. I will modify the duration to 388 days, so the end of the analysis corresponds to the autumnal equinox. I will ensure the time increments are 4 hours and will save every 6 steps. The analysis definition is now complete, so I will close the Define Project dialog. The second step required for defining the physics is to set up the material properties. Materials for a 3D GeoStudio analysis are defined using the same method as for a 2D analysis by going to Define Materials. In the Define Materials dialog, I see that materials corresponding to the geological model volumes are automatically added to my materials list. Out of these 12 materials, 3 are present in our model domain: the alluvial sand, ice-rich silt, and metamorphic bedrock. We also need to add and define material properties for the polystyrene insulation and gravel associated with the building foundation. Let us start by defining the ice-rich silt, as this material has the most detailed material definition. After selecting the full thermal material model, I will open the Define Thermal Conductivity Functions dialog, where I need to generate a curve representing the change in thermal conductivity with temperature below freezing. Here, I will add a new function named Ice-Rich Silt. Select the Spline Data Point function type and press the Estimate button. This allows me to generate an approximate function given the material type and its frozen and unfrozen thermal conductivity values. I will select the silt sample material type, enter 0.00232 kilojoules per second per meter per degree Celsius for the frozen conductivity, and specify the unfrozen conductivity to be 0.00149 kilojoules per second per meter per degree Celsius. After pressing OK, I see the function in the graph portion of this dialog. The thermal conductivity decreases from the frozen value to the unfrozen value, following an exponential pattern. For reference, the thermal conductivity of ice is nearly 4 times larger than that of liquid water. I will close this dialog and select the function in the first drop-down menu. Let us now create the normalized unfrozen volumetric water content function by pressing the ellipses button, adding a new function named ice-rich silt, and selecting a spline data point function type. Again, we will press Estimate to approximate this function using the specified sample material. In this window, I will select the silt material. When I press OK, the function appears in the window, representing the estimated change in unfrozen volumetric water content relative to the total volumetric water content. After closing the dialog, I will select this function from the Normalized Unfrozen Volumetric Water Content function drop-down menu. I will now enter the unfrozen and frozen volumetric heat capacity values as 3,740 and 2,380 kilojoules per cubic meter per degree Celsius, respectively. I will set the in situ volumetric water content as 0.649. Finally, I will select the activation temperature option and specify the initial temperature of -1.14 degrees Celsius, representing the average annual ground surface temperature at the project site. The thermal properties of the ice-rich silt are now complete, so let us move on to defining the alluvial sand using the simplified thermal material model. I will specify an unfrozen thermal conductivity of 0.0022 kilojoules per second per meter per degree Celsius, and a frozen value of 0.0033 kilojoules per second per meter per degree Celsius. The unfrozen volumetric heat capacity will be 1,839 kilojoules per cubic meter per degree Celsius, and the frozen volumetric heat capacity will be 1,164 kilojoules per cubic meter per degree Celsius. I will enter an in situ volumetric water content of 0.3 and an activation temperature of -1.14 degrees Celsius, similar to the ice-rich silt. The simplified thermal material model will also be used for the metamorphic bedrock. We will use an unfrozen thermal conductivity of 0.00275 kilojoules per second per meter per degree Celsius, and a frozen thermal conductivity of 0.00279. The unfrozen and frozen volumetric heat capacities will be set to 2,175 and 2,153 kilojoules per cubic meter per degree Celsius, respectively. The in situ volumetric water content is 0.01, and we will use the same activation temperature of -1.14 degrees Celsius, similar to the previous two materials. We have now defined the thermal properties associated with all of the subsurface materials in our domain. However, we also need to add materials representing the gravel and polystyrene insulation. I have defined these two materials in a previous thermal analysis. I will open the Define Materials dialog in the previous project, select the two materials I wish to copy, right-click, and choose the Copy option. I will then paste these materials into the Define Materials dialog in my current project file. I can then click on each one to ensure the thermal properties are fully defined. Note that the thermal conductivity and volumetric heat capacity of the polystyrene insulation are quite low compared to the other materials. Our material definition is now complete, so I will close the Define Materials dialog. I will now assign materials to the domain in the spin-up analysis. Even though we have added geometry elements to the domain representing the building foundation and thermosyphon evaporators, in this initial analysis, we are assuming these are not yet present in the system. Thus, all solids above the contact surface and below the ground surface will have the ice-rich silt material applied to them. I will select all of these solids, and in the Properties window, I will choose Ice-Rich Silt from the Material Association dropdown. I will also uncheck all of the geological model volume associations in the Properties window. The top solid representing the insulation is above the ground surface, and so it will not have a material applied to it in the first analysis. I will ensure the geological model volume associations are turned off for this solid. As demonstrated in Part 1 last month, we will use the imported geological model to assign the materials to the bottom portion of the 3D domain. I will ensure that the geological model volume associations are turned on for this bottom solid. In the second analysis, I will define the materials for the bottom solid using the same geological model volume method. Similar to the first analysis, the top solid representing the ice-rich silt will have this material assigned to it in the Properties window. I will then apply the polystyrene insulation to the solid representing the top of the building base, and the gravel to the base's bottom. We should not specify a material for the solids representing the thermosyphon cylinders in this analysis, as the thermosyphon boundary condition will be applied to the outer face of the cylinders. We have finished associating our material properties to the 3D domain for both transient thermal analyses. The next step in our numerical modeling procedure is to define the boundary conditions. To do so, I will open the Define Boundary Conditions dialog as I would in a 2D analysis. I will add a new thermal boundary condition representing the geothermal heat flux to be applied to the bottom of the domain. I will select the heat flux kind of boundary and set a constant value of 8.25 times 10 to the negative 5 kilojoules per second per cubic meter. Note that the geothermal flux is the product of the thermal conductivity and the geothermal gradient. I will also change the color of this boundary condition. The next boundary condition I will add is an end factor boundary using the air temperatures from Fairbanks, Alaska. I will define the air temperature function by pressing the ellipses button, adding a new climate function named Fairbanks Air Temperatures, and selecting the linear data point function type. I will paste the climate data I have stored in an Excel file into the dataset portion of the window. In this dialog, I will select the cycle function option to ensure that these temperature trends are applied year after year. I will now close this window and select the defined function from the air temperature drop-down menu. A value of 0.5 will be used for both the thawing and freezing end factors. Again, I will change the color of this boundary condition. I now must create the boundary condition representing the temperature in the building. I will add a new boundary called Inside Building, and will set it as a constant temperature of 15 degrees Celsius. The final boundary condition that must be defined is for the thermosyphons. I will add a thermosyphon type boundary condition with a maximum operating air temperature of negative 0.5 degrees Celsius and a minimum temperature difference for vaporization of 1 degree Celsius. As I previously defined the Fairbanks, Alaska air temperatures over time for the end factor boundary condition, I can select this in the air temperature drop-down menu. I will need to also specify the wind speed over time by pressing the ellipses button, adding a new function named Fairbanks wind speed, and selecting the linear data point function type. As with the temperature data, I can copy and paste my wind data into this window. I could also bring datasets into GeoStudio using the dataset importing options. Similar to the temperature function, I will ensure the cycle function option is turned on. After closing the Define Climate Functions dialog, I will select the wind speeds I just defined. The final input for the thermosyphon boundary is to create a function representing the relationship between the convective heat transfer coefficient and wind speed of the thermosyphon condenser that is above the ground surface. I will press the ellipses button, add a new function, call it convective heat transfer coefficient, and will select the spline data point function type. I have previously defined this in another analysis, so I will copy the data points over to this window. As you can see here, when the wind speed increases, the convective heat transfer coefficient increases up to a maximum value of 0.0293 kilojoules per second per cubic meter per degree Celsius. After closing the window, I will select the convective heat transfer coefficient function. I do not need to set a surface perimeter, as I am applying this boundary condition to the faces representing the outer surfaces of the thermosyphon evaporators. Finally, I will change the boundary condition color. My boundary definition is complete, so I can close the Define Boundary Conditions dialog. To assign boundaries to the 3D domain, we follow a similar procedure as applying the material properties. I will start by assigning the boundaries in the spin-up analysis. First, I will select the face on the bottom of the domain. In the Properties dialog, I will associate the geothermal heat flux boundary to this face. Rotating the domain so I can see the top again, and temporarily making the insulation solid invisible, I will apply the N-factor boundary condition to the two faces representing the top of the ground surface. In the active permafrost protection analysis, I will apply the geothermal heat flux to the bottom of the domain again. And the N-factor boundary condition to the ground surface outside of the building. The top of the building base will have the inside building temperature applied to it. Finally, I will apply the thermosyphon boundary to the perimeter of the cylinders. To do so, I will select each solid representing the thermosyphon evaporators in the geometry list. Select the face along the length of the cylinder and associate the thermosyphon's boundary condition to this face. I can check the boundary conditions applied to an analysis by going to the Boundary Conditions portion of the Geometry Explorer and clicking through each one. When a boundary condition is selected, the geometry associated with that boundary is highlighted in blue in the 3D view. The final step before solving our analysis is to constrain and generate the finite element mesh. As discussed in the introductory slides, we will constrain specific areas of the domain where we expect greater temperature gradients to occur. I will start by selecting the ground surface. Note that you can use the selection options along the right side of the GeoStudio window for indicating the type of geometry item you wish to select. When the face representing the ground surface has been selected, I will go to the Mesh portion of the Properties window and select the Length of option under Element Edge Length. I will then enter a constraint value of 1 meter. I will then change my geometry selection preferences so I am selecting solids only, and will click on the top region representing the ice-rich silt. I will specify an element edge length of 2 meters. I can also select the geometry items in the Geometry Explorer. I will select the solids representing the insulation and gravel, and change the element edge length to 0.25 meters. Similarly, I will select the 3 solids representing the thermosyphon evaporators and will change the edge length to 0.1 meters. Finally, using the boundary condition list, I will go to the thermosyphon boundary, select the 3 faces this boundary condition is applied to, and change the element edge length to 0.1 meters. Now that I have finished constraining the mesh in specific areas, I am ready to generate the mesh. I will select the Generate Mesh icon, change the edge length to 5 meters, and ensure the dominant element type selected is hexahedral. Once the meshing procedure is complete, we automatically switch to the 3D mesh view. I can view the element types and the quality of the mesh using the visualization preferences on the right side of the window. Overall, it appears that the mesh quality is quite good throughout the domain. The mesh view is also where I define locations of interest for plotting simulation results. I will first set a location corresponding to the foundation face using the geometry location type. After pressing OK, I will rename this location so I can easily identify it in the Draw Graph dialog. I will now create a location that includes multiple points below the building for plotting temperature change over time. In the Location tab, I will use the Position Location type to enter the following points in the data table: 5,630, 428.5, 575, 5,630, 427.5, 575, 5,630, 425, 575. And finally, 5,630, 420, 575. You'll notice that these points are all in the center of the domain, with small vertical spacing below the building foundation. After pressing OK, I will name these Points Below Building. I wish to create vertical temperature profiles below the building, so I will create a new location using the polyline location type. In the data table, I will enter the points 5,630, 432, 575, and 5,630, 300, 575. After pressing OK, I will name this Center Polyline. I also wish to plot the temperature and heat rate simulated by the thermosyphon boundary conditions. This means I want to add locations for each of the thermosyphon faces. To do so, I will first select the solids representing the insulation and gravel and change their opacity to 0. This allows me to see the thermosyphons. In the Location tab, I will choose the Geometry Location type, ensure I have the Face Selection option turned on, and will click on one of the thermosyphons. I will then rename this East Thermosyphon Face. After defining these locations, I can change the opacity of the insulation and gravel solids back to 1. My project definition is complete, so I can solve the analyses. I will not solve the analyses right now, as they take over 24 hours to solve given the number of elements, the duration of the analyses, and the nonlinearity associated with freezing, thawing processes. Instead, I will open a previously solved version of this project. I will first consider the results at the end of the spin-up analysis. Temperature contours are visible on the domain, as well as heat flux vectors. 2 clipping planes were added to view the results in the center of the domain. I will unsuppress the first one. The temperature contours are not linear as I had originally expected. I can quickly go to my Draw Graph dialog and open the convergence plot to check that convergence was reached for all steps of the spin-up analysis. There are no convergence issues indicated here, so I will close the dialog and consider my results in more detail. You will notice that the nonlinear temperature contour in the center of the domain is reflective of the sloping contact surface between the ice-rich silt and the underlying materials. Thus, the geology at our project site had a larger than anticipated influence on temperatures below the ground surface, and indicated 3D heat transfer was present even without the presence of the building. Let us consider the results from the active permafrost protection analysis. We still have the temperature contours and heat fluxes illustrated on the domain. I can click through the time steps to visually review the results. I will open the Draw Graph dialog to view results from the locations we set before solving the analysis. Similar to the first analysis, there do not appear to be any convergence issues in the second analysis. I will then select the temperature over time plot to consider the change in temperature at discrete points below the building. Note that in the Location dropdown, I selected the location that we created in Mesh View and named Points Below Building. I then selected Temperature versus Time in the Parameter dropdown menus. As expected, the temperature at different elevations below the center of the slab changes sinusoidally with time. The amplitude of the changes is smallest, and the phase or time lag is greatest at depth. Here you can see that the point closest to the ground surface exhibits a dampened sinusoidal temperature trend that follows the air temperatures applied to the ground surface. I will also take a look at the temperature profile plot through the center of the domain. The straight line here represents the initial temperature conditions we set at the beginning of the spin-up analysis. Seasonal temperature trends affect the top 20 meters. However, below this, temperatures do not change sinusoidally throughout the year. Below the gravel layer, the ice-rich silt appears to remain frozen throughout the year. There is a slight increase in temperature with depth. This matches our expectation for the results given the heat flux applied to the bottom of the domain, representing the geothermal gradient. Let us take a closer look at the results from the active permafrost protection analysis. Here you can see that the temperature varies along the length of the thermosyphon evaporator. Consequently, the heat rate varies along the length of the evaporator due to these spatial differences in temperature. Heat flow over the entire thermosyphon evaporator face was summed. As you can see here, the sum of the heat extraction rate along the length of the evaporators varies with time due to temporal differences in air and surface temperatures. The results from all 3 thermosyphons are similar, which is indicative of proper placement. You will recall that the thermosyphon evaporators were placed such that they each had the same contributing surface area. As expected, the thermosyphons are inactive, indicated by 0 heat extraction rate values when the air temperature exceeds -0.5 degrees Celsius. This was the maximum operating air temperature defined in the thermosyphon boundary condition. Finally, a closer look at the temperature in the gravel layer reveals near constant temperature across the layer over time. This indicates that the thermal conductivity of the encasing material enhances the effectiveness of the thermosyphons. This concludes our webinar on conducting a three-dimensional heat transfer analysis in a complex geology. As we learned today, the methods for adding analyses and setting up our material and boundary conditions are the same in Temp3D as in TempW. Materials and boundary conditions can be easily applied to geometry items using the Geometry Selection Tools and Properties Definition window. As in 2D analyses, we can constrain the 3D mesh where high temperature gradients are expected. The mesh view also allows for the ability to set locations for plotting results. Finally, there are similar tools available for interrogating 3D analysis results as for 2D GeoStudio analyses. Resources related to this webinar are available online. An online Build3D course is available through the Sequent Learning portal. The only thing required to take this course is a Sequent ID, which can be generated for free. Multiple 3D example files can be downloaded from the GeoStudio website at geoslope.com. To learn more about GeoStudio, there are also many tutorial videos, engineering books for each product, and past webinars available on the GeoStudio website. We have now reached the end of this webinar series. A recording of this webinar will be available to view online. Please take the time to complete the short survey that appears on your screen so we know what types of webinars you are interested in attending in the future. Thank you very much for joining us, and have a great rest of your day. Goodbye.